to tell you about causality bounds, which is work I've been doing together with Claudia Derem and Andrew Tolley at Imperial. And it's just a series of works on understanding how to put bounds on effective field theories. So perhaps one of the questions for the audience here is, why do you care about effective field theories in gravity? And the reason, quite obvious, is, GR is a non-renormalizable theory. So the way to think about it as a quantum field theory is to think about it as an effective field theory that has higher order corrections besides just your Einstein-Hilbert term. So eventually the goal of this program is to be able to bound coefficients of gravitational theories. But today we're going to start with the basics and do it for scalar field theories and also for effective field theory of a photon. So let's start with the question of what is an effective field theory. So generically, you can just write the Lagrangian as a series of all the operators that are consistent with whatever symmetries you decide that your effective field theory has. And here, for simplicity, I'm deciding that it only has one scale. This scale would be the cutoff of your effective field theory. So for example, here lambda. So your theory is valid for energies under this scale. And at higher energies, then you have the UV completion that you do not need to know since we're taking a bottom-up approach here. And here you're just going to write all of these operators and with some coefficients in front that are called the Wilson coefficients. And for these coefficients, in principle, the effective field theories just tell you that that can take any value you want. But it is very well known that not every value is physical. So the question is, how do you find out which values are physical and which ones are not? And here I just put a simple example of what I mean by an effective field theory. So again, just the simple scalar field, you will just have its kinetic term. And if I said it has a shift symmetry, so if you do phi plus a constant, then it's invariant under that, then you have higher derivative corrections that are just derivatives. So another important question is, why do you even care about knowing what are the values of these Wilson coefficients? So this is a more phenomenological question. And the reason is that if you actually want to go ahead and look at experiments and make some measurements and put priors on what you're going to find here, it is very important what priors you use. So your priors could change a lot what are the bounds that you infer on these coefficients. So if you want to bound theories beyond GR, for example, so this is an example of a plot here. Don't worry too much about what each axis is. But the idea is that if you put no priors at all, you will get the orange bounds. If you ask for just subluminality, you will get the red bounds. If you put positivity bounds, which I'll explain in a second, this actually shifts drastically and you get now bounds on this side. So it basically tells you, if you assume certain physical requirements of your effective field theories and put this as a prior when you actually analyze data from experiments, you can find very different results. So it is very important to tell the experimentalists that actually do this data analysis what are the correct priors to use for your theories. And the question is now how to tell them what are these priors. So you have several options, and this is really a matter of what you believe is the true theory. And one of the most stringent options could be deciding that you want that the UV completion is a string theory. So if you decide this, then your UV is going to be string theory, and you can have bounds on what are your coefficients by these Swampland conjectures. So that's one option. If you don't want to have so many constraints as saying the UV theory is a string theory, you can relax this a little bit and say you want that your UV theory is local, unitary, causal, and Lorentz invariant, which makes sense. It's very reasonable. And if you don't want anything exotic, probably true. And this goes under the name of positivity bounds, which I'm actually not going to go into details today, but I'll show you some examples of what are the bounds in the parameter space, but not exactly how they're computed. But let's say that you want to relax this even more and not do any assumptions on your UV, which is basically the idea of effective field theories. You just don't know anything about your UV. You just want to have some symmetries in the IR. And just based on that, you want to say, okay, there are some bounds on these Wilson coefficients. So this is what I'm going to tell you about today. And the idea is to check if you have causal IR propagation of modes of your theory. So I'm going to move on and explain what that means. And so far, any questions? Okay, good. So now I'm gonna go a bit slower to explain exactly what I mean about causality in the IR. So there are many different versions of what you can refer to as causality. One of them being microcausality, which implies in a classical limit that your Green's functions have only support inside your light cone. So that will be 0 if you're outside of your light cone. So that would be one implication that you want of causality. Now, you can go and compute these Green's functions. That could be a bit complicated depending on your theories, or you can go and compute some observable that basically measures how far or what is the support of your Green's function. And this observable actually is the time delay. So you can go and look at time delays, which have a very well-defined form in terms of an S matrix that you can look at here. And basically the idea is gonna be that I'm gonna take an effective field theory. I'm gonna assume that there is some non-trivial background for this field. So I'm gonna call it, let's stay with a scalar. So there's gonna be a phi bar, that's a non-trivial background, so not 0. And there's gonna be modes of this scalar field propagating around that background. And what I want is that all the modes that propagate around this background are causal. So you don't have closed time-like curves forming with this propagation. And as long as you assume that the light cones that tell you what is causal are given by a high energy photon, so just like the speed of light is what determines causality. If you have certain bounds on the time delay, that will imply that you don't have closed time-like curves. So I'll show you in a second what are those bounds. So again, we're only gonna work in the infrared. So we're gonna work with low frequencies because we don't wanna go beyond the limits of validity of the EFT. And we're gonna, in like a cartoon way, compare what will be the propagation of your EFT modes that are gonna be modified around this non-trivial localized background. So it has asymptotics that just go back to trivial. So you can have like proper scattering and your asymptotic states that you will usually think of. And you're gonna compare the light cones of that versus the light cones again of a photon that just had the speed of light.
Sorry,
Yes.
is your statement here that I can start from the box up there and get the time delay has to be positive?
You can think of the time delay as a measurement of what is the support of your retarded Green's function outside of the light cone. And by it, when I say light cone, I always mean like actual light cone by the photon. So that's the statement. So a bit schematically, what you're gonna end up finding is you're gonna have this background phi bar. You're gonna look at the perturbations around this background. So it means that now your kinetic terms that you look for these perturbations now have some effective metric due to this background. So this is just very standard. Just think that you have perturbations around Schwarzschild. So now your perturbation sees some different kind of effective metric produced by your Schwarzschild black hole. So that means that they see a modified light cone, and you can actually compute what would be like the speed of sound that they see just by simply looking at the structure of this modified light cone. And in principle, you will think, okay, I just want to bound the speed of sound of these modes. I just want to say, I don't want to have superluminal modes. If they're all subluminal, that should be good enough. And then my theory is causal. And yes, that's true, but it's too restringent. And the reason is because there's actually, you can allow a little bit of superluminality in your theory, and it will still be physical. The thing is that you don't have to have the superluminality for long periods of time or for long regions, such that this builds up to give you a time delay that is observable. And this is a feature of basically quantum mechanics, and a bound that we're gonna find is actually proven strictly in quantum mechanics. For quantum field theories, it's more of a evidence-like bound, but nevertheless, we use it in a similar way. So the time delay is gonna be more of a measurement of the whole propagation of your modes, not just at a given time. So it doesn't matter, again, if the speed of sound goes superluminal at just one point, but for too long. And having a time delay that is resolvable means that you can actually measure it. So now you send a wave, the wave has a wavelength lambda or energy omega. And now if you want to probe something after this wave scattered, by uncertainty principle, you will not be able to probe anything that is smaller than this lambda. Which means that if I find a time delay that is positive, aka it moved faster than the speed of light, but it's very small and it's smaller than lambda, you cannot measure this. Is that clear for everyone? So you're allowed to have a little bit of superluminality. Yes?
It's 1 second. You mean the group velocity doesn't have to be superluminal in some sense? When you mean long average of
It's,
time,
yeah, it's definitely not the,
not the local velocity, the group velocity.
and yeah, so you can have superluminalities. I mean, it's known in many condensed matter systems, they have been observed. It's just, sorry, you're thinking about group velocity versus phase velocity.
Yeah, yeah,
Phase
yeah.
velocity versus luminar.
Yeah, exactly.
No,
I'm saying the group velocity doesn't have to be superluminal.
phase velocity doesn't have to. I'm saying phase velocity can be superluminal. Okay.
Negatives.
Yes. Yeah, I'm saying here phase velocity can be superluminal if it's not for too long. If it's for too long, it will give you a time delay that will be observable. So you just have to make sure that you do not obtain something that you will be able to resolve in an experiment and that is not given within the uncertainties and that your experiment can be able to measure. Yes.
Yeah, sorry, I'm just thinking about like hard sphere scattering or something. I guess you're looking at.
Yeah, so I'm gonna exactly get to that. Hard sphere scattering will give you something different. It totally violates this one. So I think in a second I'll get to that, but yes, you should not be thinking of this bound applicable to hard shell scattering. That's totally true. So the bound that has been proven in quantum mechanical systems is this one over here. For quantum field theories, you don't have a proof that I will say is valid for every QFT, but the expectations is that this holds with an order 1 number on the right-hand side. So this is the bound that we're going to be applying and for all our effective field theories. Now, if you include gravity, things get a bit more complicated. And what happens is that, as you all know, you have a Shapiro time delay. So let's say you have an effective field theory, and a scalar effective field theory living in some gravitational background. Besides just having a time delay that will arise from the effective field theory corrections, you're also going to have a Shapiro time delay. So there's a question of what should be now the bound on the full time delay or only on the EFT corrections. And this is a matter of choice of what you think you should be comparing now light cones with. So this basically tells you you're comparing with the light cones at spacetime infinity, aka the light cones of a flat universe. This bound over here says that you should be comparing causality for not having support outside of the light cones locally. So if there's a photon that is just traveling locally nearby a Schwarzschild black hole, we know it's going to get a Shapiro time delay. We want that the EFT corrections actually don't propagate outside of the light cone of this photon locally. So it's kind of a local versus asymptotic. So this one goes under the name of asymptotic causality, and this one goes under the name of infrared causality. There are some proofs for this one from scattering amplitude methods, but they're not fully for any gravitational system. For this one, there's evidence because there are theories that satisfy this, such as effective field theories for electrodynamics in coarse spacetimes. So there's evidence for both. And again, it's a matter of choice, in my opinion, which one you decide to apply and not a full definite answer which one's the correct one. But today we're not going to talk about gravity because the program that I'm going to show you is some application of these methods, but to bound higher order coefficients of EFTs, which tends to be complicated. And this is gonna be on scalar effective field theories, so work that I did with Claudio Derram, Victor Pusquet, and Andrew Tolley, and on photon effective field theories, so same people plus Sumer Yagley and Anna Tokareva. So first one, just very quickly, our scalar effective field theory will be the theory of a scalar that has a shift symmetry. So the first three corrections for this will be of the following form. And we're gonna assume that there's an external source coupled to your theory that will indeed break the shift symmetry if you want, but you could also build something that does not break the shift symmetry, and you can just break it weakly. Now, these operators that I have here are dimension 8, 10, and 12. Whenever you compute the speed of sound for these kind of modes, of course, as we know, higher dimension operators in an EFT are expected to be suppressed. So this is the reason why it's hard to put bounds on these coefficients over here. It's very easy to put a bound on the first coefficient, has been done many years ago. But from this perspective, it's very hard to put bounds here because their usual contribution to the speed of sound is expected to be small just by EFT arguments of having higher and higher order operators in your EFT being suppressed. So I'm gonna show you what is the caveat on that. So again, take some background, 5, and there's gonna be a perturbation here, your curly phi. Let's assume for a second that these are just plane waves, the perturbations, and we're always gonna work in the limit where you have a separation of scales between the background having a very large wavelength and perturbations having a very short wavelength. And we want this because otherwise you would not have a well-defined phase shift and hence a calculation of a time delay. And this is why hard sphere scattering will not be allowed in here. Hard shell scattering will actually give an additional term that looks like violations of causality, but it's very well understood. It's just basically the rebound from the shell. So nothing related to causality. We want to exclude the cases where you could have such kind of scattering because then you cannot separate the physics from just reflection and actual violations of causality. So this helps us avoid that problem. So let's just look at what would be the calculation of that speed of sound for these waves living in this non-trivial background. So schematically, again, they will look like the following. At leading order, as I said, it's very easy to bind these coefficients. This was done in this Adams et al. Paper from, I think, 2006 or 2016, I can't remember anymore, but a long ago. And it's known that this contribution will always be positive definite, which means that if you want this to not violate causality, in fact, you want the coefficient G8 to be positive. And we can just fix it, which means fixing what is actually the cutoff of your theory. So I'm going to work with G8 being actually equal 1 in the rest of the talk. So I'm just going to put bounds on G10 and G12. G12 also tends to be, it's just positive definite. And G10, on the other hand, can have either sign. So that tells you that you could have bounds from both directions on these kind of operators. Now, again, the reason why we can put bounds on higher order coefficients is because we're gonna do a fine tuning of your background. So while these are definitely EFT suppressed with respect to the leading order operator, which is this, these also depend on what background field you have. So you can pick a specific background field such that the derivatives that appear here in this specific combination are enhanced, while the derivatives in all of the other operators are still order 1. So let's say you make these derivatives order 10 and everything else order 1, and now the largest contribution comes from this operator. And you can do the same for higher order operators, and you can do this while keeping the EFT under control. So that's the magic trick on how to bound higher order operators in effective field theories. It's playing with fine-tuning your background so that you can find a specific case where this is the largest contribution.
Those pies are all 5 bars, right?
Those 5 should all be 5 bars, correct. Thank you.
G10 always, I mean, you said that you were considering both cases, but this is because you are doing IR inference.
Yes.
You use the other one of the others that you are not gonna mention, in these cases, there should be positive. Is that correct?
For G10, you mean? I'm gonna show you what are the bounds for positivity on this case. So there actually is gonna be bounded from both sides too.
Maybe a technical practical question. So you want this high frequency probe sent in order to solve the equation for the propagation in some sort of WKB or Icona-like method.
Correct. Yeah. So I'm gonna work on WKB just because it's a bit more general and I can take a small multiples too. So yes. So the general formula is gonna look again schematically like this. So that idea of having the time delay bounded to be not too negative, it's gonna look like the following. The omega is basically 1 over the lambda of the perturbation. There's gonna be a length scale from the background that just arises from integration around your space-time regime that you're gonna be propagating through. And leading order corrections, you just have basically the difference between the speed of sound and the speed of light. So the point here is gonna be that by just assuming that you have a valid EFT, these corrections are always gonna be small. So it's a competition. This is small. And on the other hand, we're gonna have a WKB regime. And that means that this is gonna be large. It's just a competition between these two terms to see if they can become large enough to lead to violations of causality. So the general setup is gonna be an spherically symmetric background. I'm just gonna consider some special function that I'm gonna tune. And what you're gonna find is the equations for the perturbations. Since it's spherically symmetric, I'm just gonna look at the radial perturbations. Are gonna have some equation of motion that looks Schrodinger-like. You solve them using WKB methods. And you find your phase shift and hence your time delay. So overall, the usual structure. And here, this specific form of this function that you have over here is what determines why you had the structure before of having the speed of light and the difference between the speed of sound appearing in the proper way. But it's important also to notice that besides the speed of sound, there's also an effective potential contribution, but it's WKB suppressed. But it can help us still bound coefficients. Yes.
The equation of motion for the background, do you include the higher order operators in the Lagrangian?
So for the equation of motion for the background, I just assume that the background is gonna be satisfied by this, and there's just some generic external source that allows you for that. So all I end up doing is assuming that there's this weird external source that does satisfy the equation of motion with all the higher order operators. Then you can check, once you pick your background, you can check what source you would need, and then you can check that the source is physical. So it's not that the source is giving you violations of causality, but that the theory actually has violations of causality. So it's more of a, we pick the background and then check the source is okay. So recap, we have a WKB expansion. And also we have an EFT expansion that the operators that have higher order derivatives are gonna be suppressed. So in general, you are working on a high frequency limit for the WKB, but not too high that it breaks down on the EFT. So there's some small parameter that kind of bounds what actually are the frequencies that you work with. And you have to be very careful because you want validity of the EFT and you also wanna work on the WKB regime. So results. So this is what I was saying. Here is the bound between G10 and G12. Positivity bounds will lead to the yellow region. Causality bounds lead to the blue region. So it's very nice to see that it's very close to the positivity bounds. It's also interesting because positivity bounds have more assumptions than causality. But in this simple example of the scalar, we're able to reproduce almost everything. And by almost everything, I mean because the G12 direction, we weren't able to find a bound in there, mostly by issues of extending our WKB to higher orders. But I'd say there's a chance that one could find a bound there. And in the last 5 minutes, I'll quickly mention what happens with the photons. So any other questions before I do that? Cool. So let's check photons now. Here, the Lagrangian is horrendous, so let me just explain the effective field theory with amplitudes that I'm sure you are all happier with. So basically, again, I'm gonna have dimension 8 operators that are like an f to the 4, dimension 10 that are like d square f4, and dimension 12 now for derivatives on them. And of course, now you have helicity amplitude, so you have to be careful to check each of those terms. So what we're gonna do now for the bounds is that, again, we're gonna take a spherically symmetric background. So you can just think of an electric background that has some spherical symmetry, and it just, we're gonna tune again the background a little bit to find the bounds, but it decays again to 0 at infinity. And since, of course, we have 2 modes for the photon, now we have 2 time delays. In this setting for spherical symmetry, it's just gonna be like the even and odd modes. So what you're gonna have to make sure of now is that, sure, you have many more operators, but you also have more constraints because you have 2 modes propagating, the odd modes and the even modes. So you're just gonna check that all of them are causal, aka satisfy the bound that I showed you before, that is not too negative. Now here is an ugly table that basically tells you if the contribution to the time delay of all these operators is gonna be sign definite or not, which tells you if there's like a 2-sided bound operator or if it's just positive. And similar to the scalar case, there's gonna be some operators here, what I called G2, it's gonna be similar to the G8 one for the scalar, it's just gonna be positive, it's the leading order and it just defines the scale of your theory, so I can get rid of that. And there's gonna be a term that's similar to the G12 that I wasn't able to find a bound on one side, but it was WKB technicalities. We also have something similar in this case. The rest are just gonna be not sign definite, so we find 2-sided bounds. Now, of course, your Wilson space coefficient space is enormous now, so I just show some of the slices. Simplest case that was found again in Adams et al. A while ago is on these leading order operators. Positivity bounds gives you exactly the same. So leading order, you simply reproduce the same, but this was known. Then you can go to higher orders and check if some known partial UV completions. So for example, your standard QED. So if you just integrate your spinner and you see like an effective field theory of the photon fits in your causality and positivity bounds, and they do. So here causality is solid and positivity will be dotted. So causality is not as good as positivity, but it still helps in some regions. So it's nice. But more interestingly, in some case, like in slices where there's like a partial UV completion of a photon interacting with a scalar or with an axion, and you integrate out the scalar or an axion, you find that there's a complementarity between imposing causality bounds and positivity bounds. So they basically give different regions of bounds, and if you combine them, you find a very, very small region, like only this line or only this triangle over here. Now, let me make clear that the positivity bounds that we use here are analytic and not the strongest numerical ones. It doesn't mean that positivity and causality do not agree with each other. It just means that if you don't want to use the full numerics of positivity bounds, which tend to be quite complicated, and you just want to use analytic results, you can combine both methods and get very sharp answers. And I'm probably just going to skip this and end with review of what I just told you. So the nice thing about infrared causality is that you have to use UV assumptions. In some cases, it gives you complementarity with analytic positivity bounds. And here I just show you how to test operators that have 4 fields because I wanted to compare to positivity bounds. But positivity bounds are not well known for more than 2-2 scattering. Causality can be very easily applied beyond 2-2 scattering, so that's an advantage. And it can also be applied to cosmological settings, which also positivity, we don't know very well how to do that. So future directions, of course, is to do this for higher dimensional gravitational operators. Thank you.